I want to talk about socially fair k-means clustering. This is a joint work with Merta Adui and Santosh Vempala, who are both at Georgia Tech. Let me start by giving you an outline of my talk. I'm sure that many of you are familiar with k-means clustering. It's a very basic clustering algorithm that is used not only in computer science, but in many other domains as well. But still, I will give a brief overview of k-means objective and Lloyd heuristic, which is probably the most widely used heuristic in practice to get a solution for k-means. Then, using some synthetic and real-world data, I will motivate why in some scenarios the vanilla k-means objective and Lloyd heuristic algorithm can result in a clustering of the data that is less favorable to some demographic groups. This motivated us to define a notion of fairness for clustering and specifically for k-means. And the main contribution of our work is that we introduce a modification of Lloyd algorithm that is simple and efficient and can be used in practice if our notion of fairness is something meaningful for the application context. I will conclude by showing some empirical results of how our algorithm performs in practice and some generalization and open questions. Okay, so if you don't know what this k-means, probably this is an important slide. We are given a set of points U and we want to cluster it into k clusters, right? So we want to partition your data into k disjoint subsets. And how do you want to do this clustering? K-means objective says that you want to find k set of centers, so k data points in your set. They don't have to belong to the set, so you want to find k set of centers such that if you assign each data point to the closest center, so this induces a partitioning on the data, then you want to minimize the square distance of each data point to the closest center, right? K-means objective is NP hard to optimize, and in practice, Lloyd heuristic is probably the most widely used algorithm to get a solution for K-means. And Lloyd heuristic is a very simple two-step process, which is the main reason for its popularity. You start with a random set of k points. There are a lot of other techniques also to initialize your k points, but I don't get into that discussion for now. For the case of simplicity, let's just assume that you start with a random set of k points and you assign each data point to the closest center. This defines a partitioning of your data. And now you update the center of each partition or cluster to be the average of data points in that cluster, right? And now you have k new set of centers, you update the partitioning, and you repeat this process. Let me give you an example on this toy smiley face data. Let's say that you want to partition it into 3 clusters, and let's say that you're starting with the blue point, with the red point, and the green point. So now if you assign each data point to the closest center, this blue, red, and green partition is the initial partitioning that you get on your data. Now we update the center of each partition or cluster to be the average of data points in that cluster. So, and then we assign each data point to the closest center again. And we continue this process. So here you are seeing iterations of the algorithm, and at the end it converges to this solution. So you have these 3 clusters and 3 centers. As I mentioned, k-means clustering has a lot of applications. So for this talk, I specifically focus on human-centric applications. And here I want to give 2 examples of customer segmentation and crime detection. So let's say that you are given a pool of customers, and for each of them, you have the data on what have been they shopping in the past few days, or what is their preferences. And let's say that then you want to cluster this pool of customers. And then for each customer, then based on their membership to a specific cluster, you want to offer them a service or a product or an advertisement. The second example is crime detection, where as a police department, maybe you want to put 4 patrol polices in one neighborhood. So you might want to partition your neighborhood into 4 different clusters and put a patrol police at the center of each cluster. So how should you do it? So how can k-means clustering and Lloyd heuristic be unfair? I will explain it by some synthetic data and a toy example, but later on, actually, I will show you some real world experiments as well that shows similar observations. Let's say that you're given this data set, and let's say that you have 2 demographic groups in your data. Let's call them blue demographic group, which is the majority, and purple demographic group, which is the minority. And let's say that you have resources only to build 2 schools for this population. So for this reason, you want to partition your data into 2 clusters. So on the left-hand side, you see the result of Lloyd heuristic. So I have these 2 clusters, and the 2 dark blue points are showing the centers. Now, if I look at the blue data point, on average, the square of distance of a blue data point to the closest center, it's actually pretty good, and it's not far from the optimal that you can achieve for that population. And what do I mean by optimal for that population? Let's assume that there were no purple points in the data. Then if you wanted to find 2 clusters only for the blue population, then you would have ended up with the center of these 2 probably Gaussians, and that would not have been too far from the solution that we have right now. On the other hand, for a data point in the purple population, the access cost to the closest center, or the square of the distance to the closest center, is pretty high. So this solution in terms of access cost is not very good for them. On the right-hand side, I'm showing you another clustering, which is actually putting all the blue points in one cluster and all the purple points in another cluster. And I'm showing you the corresponding centers. And as you can see in this clustering, the access cost for the blue demographic group has increased, but the access cost for the purple demographic group has decreased. So this is a more equitable solution for these 2 demographic groups. And later on, at the end of the talk, I will come back to this example, and we can discuss what are the scenarios that this notion of fairness could be meaningful, because as you can see, I ended up with a cluster, with a clustering on the right side that has only blue points in one clustering and only purple points in another clustering. So in terms of demographic diversity, this clustering is terrible. We will come back to this. But for now, let's just stick to our notion of fairness, which wants to have a clustering that has equitable average clustering cost across different demographic groups. Okay, so this was a toy example, but we have similar observations from looking at some real-world data sets. I'm showing you some examples from adult data set and credit data set. So the x-axis is showing the number of clusters, and the y-axis is showing the average clustering cost. So for example, if you look at the left figure, the purple line is showing the average clustering cost for a female individual. And the blue line is showing the average clustering cost for a male individual. And as you can see, these are very different. And by the way, I'm not assuming binary model of gender here. It's just simply that these 2 labels were the only labels that were provided in this data. So this was if I partition my data based on female and male. This adult data set also have 5 racial categories. What if I partition my data based on these racial categories? Then actually the situation gets actually worse. So as you can see, the average cost of clustering for an Asian Pacific Islander, if I use the vanilla k-means algorithm, so Lloyd heuristic, is 4 times worse than the average cost of clustering for a white individual. And we saw a similar result for the credit data set. Okay, so how can we address this issue of bias with k-means objective and Lloyd heuristic? We propose a notion of fairness for clustering, and then we study it for k-means clustering. Before getting into this notion of fairness, I should give you a simple definition. So given a partitioning of your data, U, so here, for example, you have the blue partition U1, the green partition U2, and the red partition U3, and 3 centers C1, C2, and C3, then the cost of partitioning U with respect to these centers, C1, C2, and C3, is simply defined as the sum of the square of distances of each point to their assigned centers in their partition, right? So it's similar to the k-means clustering cost, or the sum of square distance cost that we usually use. The only difference is that this is a bit more general, because here I'm not assuming that my centers are the average of the points. Even the centers don't have to necessarily be the closest to the data points that they are assigned to. Okay, now using this definition of cost, we define the fair k-means objective as the maximum average clustering cost across different demographic groups. So for the sake of simplicity, for now, I assume that I have 2 demographic groups in my data. Later on, I will show how our results can be generalized to M demographic groups. So for now, let's assume that you have demographic group A and demographic group B. Then here, so you're given a partition in U, and C is the set of centers, right? So you are calculating the cost of the clustering induced on demographic group A with respect to center C on average. And similarly, you are calculating the cost of clustering induced on demographic group B with respect to center C on average. So I want to look at this, the maximum of this average clustering cost for these demographic groups. And the optimal solution for the fair k-means objective is looking for the minimum for the clustering and the centers that gives you the minimum maximum average cost. Now going back to our toy example, comparing the cost max for these 2 different clusterings on the same data, for the clustering on the left hand side, the cost max is the square root of the dashed red line. So it's the average access cost that a purple data point has to get to the closest center. But for the right-hand side clustering, the cost max is the square root of the blue dashed line. So as you can see, for the right-hand side clustering, the cost max is smaller compared to the left-hand side clustering. So we call this social fairness, but this is analogous to the notion of min-max fairness that actually we came up with a couple of years ago and studied it in the context of principal component analysis and dimensionality reduction more broadly. There was Abbasi et al. Studied this notion of fairness independently for k-means and came up with same approximation algorithms as us. They also studied it for k-median and facility location. Min-max fairness has been studied in other contexts, including classification and regression as well. Okay, so the main contribution of our work is that we introduce a simple modification of Lloyd heuristic that can be used in practice to obtain fair solutions. So how does our algorithm work? So we initialize a set of centers at random or using k-means plus plus or whatever method that you want to use. So far it's exactly identical to Lloyd heuristic. And then it's again a 2-step iterative process. You assign each data point to the closest center. So this defines a partitioning of your data. And now remember that in the vanilla Lloyd, now we updated the centers of each cluster to be the average of data points in that cluster. Now, instead of setting the center to be the average of data points for that cluster, we find the fair centers, which are the solution to the cost max objective. So given this specific partitioning U, and now I find K set of centers C such that it minimizes the maximum average cost over 2 different demographic groups A and B. So the main technical question is that how can I do this fair center update efficiently? And this is what I briefly discussed for the case of two groups right now. So our main lemma is that for a cluster UI, if you consider mu I of A to be the average of demographic group A on cluster I, and if you consider mu IB to be the average of demographic group B on cluster I, then we actually show that the fair centers are on the line segment that connects the average for demographic group A and the average for demographic group B. And this is by a simple contradictory argument. So for the sake of contradiction, let's assume that the fair center is not on this line segment that connects the average of demographic group A and demographic group B. So let's say that the fair center is CI. Then I can write the cost of population A in cluster I with respect to CI as simply the cost of population A in cluster I with respect to their average plus the size of population A in cluster UI times the distance between the average of population A in cluster I and CI. This is a general fact that we know about all these, like a sum of square distance costs. Similarly, for population B, the cost of population B in cluster I with respect to CI is the cost of population B in cluster I with respect to their average plus the size of population E in cluster UI times the distance between the average of population B in this cluster and CI. Okay, and now the argument is very simple. So if CI is the fair center, now I project CI to the line segment that connects these two averages. And you can see that both of these terms, you can reduce their value, and therefore you are reducing the maximum cost by using C prime I instead of CI. Okay, so the fair centers are simply on the line segments that connect the average of demographic groups in each cluster, and therefore now I can rewrite my min-max optimization as following. And now I simply only need to find the location of these fair centers on each cluster. Right? So on the cluster I, if I look at the average for demographic group A and the average for demographic group B, I just need to find the distance xi between CI and, say, the average for demographic group A. And now if I rewrite my min-max optimization in terms of these distances, I simply have these two terms, and therefore my center update is a convex problem. Okay, so this is a convex problem. I can solve it efficiently by convex programming, but we actually show that we can solve it much faster. So for the case of two groups, we show that we can find a fair center using a line search on a one-dimensional curve. I'm not getting into the details of that. But the implementation of our fair lloyd algorithm is actually based on this line search and is publicly available. Okay, furthermore, our fair k-means solution is stable, which means that, of course, we are guaranteeing that the group with the maximum average cost cannot improve their cost at the optimal solution. But furthermore, we even show that the group with the smallest cost smaller cost cannot improve. In other words, our solution is on the Pareto frontier. Our fair lloyd algorithm converges to a local optimal, and furthermore, if you have an alpha approximation for k-means, this naturally translates to a 2-alpha approximation for the fair k-means, and this result has been shown independently by Abbasi et al. As well. Okay, so before talking about how our results can be generalized to multiple groups, let me show you how do we perform in practice. So let's get back to this example of adult data set. So remember that the x-axis is showing the number of clusters, and the y-axis is showing the average k-means clustering cost, right? So here I'm first applying some pre-processing on the data that is common in practice. So the left figure is showing no pre-processing on the data. The middle figure is showing using principal component analysis. which is very common before using k-means. And the right-hand side is showing using fair PCA as a pre-processing step, which is a modification of PCA that is using the min-max objective to find a low-dimensional representation that has more equitable reconstruction error for two different demographic groups. Okay, so let's look at the left figure. The purple line is showing the average clustering cost for a female individual in the data, and the blue line is showing the average clustering cost for a male individual, and the yellow line is showing that the average clustering cost achieved by fair Lloyd, which is equal for these two different demographic groups. And we saw similar results across using different pre-processing techniques as well. So as you can see, the fair Lloyd is closing the gap between these two average costs. So in terms of running time, we are doing only a bit worse compared to vanilla Lloyd. And also in terms of convergence, we are almost the same as vanilla Lloyd. Okay, I talked about our algorithm for two groups. The k-means objective could naturally be defined for k groups. You want to find a clustering such that you want to minimize the maximum average cost for m different demographic groups in your data. For the case of two groups, we've shown that the fair centers are actually on the line segment that connects the average of demographic groups in each cluster. For the case of m data points, we show that the fair centers are in the convex hull of the average of these m demographic groups in each cluster. And therefore, again, we have a convex problem. So let's go back to the adult data set. So for the case of two groups, I considered male versus female. Now let's see how do we perform if we consider our demographic groups to be the 5 facial groups that were provided in this data. And here the x-axis is showing the number of clusters, and the y-axis I'm showing the ratio of average clustering cost between every pair of demographic groups. And as you can see, using the vanilla Lloyd, the purple line, the ratio of the maximum ratio of clustering costs between two demographic groups is really high. And we saw that at the beginning of the talk. For Asian Pacific Islander, on average, the cost of clustering was like 4 times more than a white individual. But using the fair Lloyd algorithm, after 20 clusters, we are getting the ratio of 1, which means that the average clustering cost for all the racial groups is equal. We have similar approximability results. So for M groups, if you have an alpha approximation for k-means, this translates to an M alpha approximation for fair k-means, and our solution is a stable and fair algorithm actually converges to a local optimum. Okay, so in conclusion, we talked about k-means, and I showed some human-centric applications where k-means could result in a solution that is less favorable for some demographic group in the data than the others. Then we proposed a min-max notion of fairness for k-means, and very importantly, we defined a very simple modification of Lloyd that could actually be used in practice to achieve a fair solution. So for people who are interested in theory, the interesting questions are whether we can get better approximation factor for fair k-means. There have been papers since then that already improved our approximation factors. For the case of two groups, we have this really super fast center update because we are only doing a line search on a one-dimensional curve. But for the case of M groups, we don't know how to do that. It would be an interesting question to explore that. And finally, as I promised, I come back to this example that I showed at the beginning, and hopefully this could be a point for discussions and after the talk. So when we talk about the min-max fairness, the notion of fairness that we discussed during this talk, the clustering on the right is more equitable compared to the clustering on the left, but it's resulting in a clustering that has zero diversity, right? One of your clusters is only the blue points, the other cluster is only the purple point. And in general, it would be interesting to study whether our notion of fairness is in conflict with the other famous notion of fairness for clustering, which has been proposed by Chirichetti et al., referred to as proportionality of clusters, which essentially means that whatever distribution of demographics you have in your data, you want to have that distribution in each of your clusters as well. And furthermore, what are the real world data assumptions that might allow you to achieve both of these? So individuals have equitable access to the facilities, but at the same time, you have diverse schools, for example, if you want to build the schools at these facilities. And the other concern here is that clustering on the right, if you actually want to build two schools here, the top clustering is very populated, right? You have a lot of data points in that clustering, and the bottom clustering, you have very few data points. So what if you want to also put a constraint to have clusterings that have similar or the same size? Thank you so much.